to give that international flavor to it. So what I'm going to talk about, as John says, is plastic contamination of the oceans. And the big question is, are we in crisis? Now, we've all been hearing, whenever you look at the newspapers about this, it's a crisis. The oceans are being destroyed by this material. The oceans are absolutely collapsing under the weight of plastic that's being put into it. So I need to ask that question. Are we in crisis? So in fact, 7 years ago, I set up a research group, the Microplastics Research Group, in order to really address this question. Is it something we should really be worried about, or is it just, it doesn't look very nice? It clutters up the beaches. So that's and how does this balance this level of crisis with environmental change, global warming? How does this balance? You know, what is more important? So, so what I do is say words about this wonderful material, saying about the issues which I see are important in terms of it, whether it is actually doing harm. And talk about the work that my research group has been doing, and then come up with some positive words at the end, things that we can do as individuals. And that is an important part of it, because we can do things. We don't just have to sit on our thumbs and moan about it. We can do stuff. So first thing is, plastic really is a wonderful material. It is quite extraordinary. I mean, it's lightweight. So for instance, our cars are lighter, so they use up less fuel. It's inexpensive. It's durable for making underground pipes, for instance. It's really versatile. So it's got enormous number of properties which make it really attractive. And in every day of our lives, we come across it in numerous types. I mean, the database we have, for instance, 14,000 types of plastic in it. So it's a really common material and very, very versatile and excellent. So we've had 6 years of research and development into this material, and we've had 6 years of behavioral training to throw away. Not smart, really not smart. This came from Life magazine back in, I can't remember, it was 1960 or something like that. And so this was saying, this is great material. You just get a plate, you put some food on it, you eat the food, and you throw it away. Isn't that wonderful? Isn't that just a great way of living? And no, it's not smart. So we're now producing large amounts globally, 400 million tons last year, 25 times more than in 1975. And we only recycle about 11% of it. Really not a good way to consider a valuable resource. So just to say something about what we do is just a pictogram showing it. We produce 8,000 million tons. We use it in various ways in society. We discard quite a lot of it, incinerate a small amount of it, and then recycle a very small amount of it. So we don't treat this material very well at all. We're not being responsible citizens the way we handle this. Now, what's happened over the last years has been analysis of how it gets into the oceans. And the big conclusion is that's where it happens. It's somebody else's fault. It's not ours, because, I mean, you look at the dots here, we don't produce much, we don't put much in the ocean. It's not our fault, is it? It's all these people in the developing countries. Those are the ones who are responsible. However, the one thing they tend to forget is that actually we in the West, we export a load of our refuse. A load of it, and what we do is we ship it into containers, recycled on the side of it, we ship it off to other countries. Let them deal with it. Then we can feel smart about ourselves. We've done our bit. We've put it in a box which says recycled. Not great ethics involved in this. So we have examples such as this, the Pasig River in the Philippines. That's a river. Now, one can do things about it by local activity, and in fact, that's what it looks like now. So with a lot of local activity, it is possible to improve these environments. So so they stopped doing it, and that then meant that we started dumping it in lots of other developing countries. But that's also being cut down. So things are actually improving. So I'm reasonably optimistic that we're doing sort of the right things.
Yes.
Good. If I need to go back one. Yep.
It's become more like a cafe discussion.
So we want to go to. Yeah, but I'm just trying to get it into presenter mode first. No, I haven't got my glasses on. So I'll get rid of that or minimize it. Right.
This is a crisis.
Yeah, that's right. I get rid of all of this stuff. Stop sharing, no. I don't seem to be able to remove this. Is that right? Okay. Is there something I should be doing about that? Okay. So the question was, is this a crisis? Well, perhaps we'll just go back to the previous grim images. And so we asked the question, this is pretty bad news. So one of the points that I was making was there's 1 million seabirds which are killed every year by plastics, by these larger particles. And here we can see one poor seabird with cigarette lighters and all sorts of stuff in its guts. And so we ask whether this is a crisis. And then the crucial bit of information in this is that if we're killing 1 million seabirds every year, is this a lot or a little? It sounds like an awful lot. In fact, there are 350 million seabirds out there, and we're killing 1 out of 350. So then you sort of put it in and you say, well, actually, that doesn't look like a crisis. As I say, I think it's probably more than 1 million seabirds, but that in itself, it's a bad number, but I wouldn't put it in the category of being a crisis. And fishing, certainly, we kill much more by fishing and eating it. So that's the macroplastics. Now, what happens to these bigger pieces, is they break up and they form what we call microplastics. And that's actually the focus of my research group. And it's also where I think the most harm is likely to arise. So microplastics, they're variously defined, but it's between, so that's 1/100th of a millimeter and 1 millimeter. So, and the human hair is about 70 millimeters or so, 70 microns. So it's about between a human hair and a grain of rice. It's that sort of size range. And these are, it's a shame we can't see the headings anymore. Can't get rid of that. Am I not on full screen? What happens if I go in here? No, that mutes it. Too difficult? You think that's full screen? No. I can't get rid of that now either. So those are the this is, yes, you did. So this is the size of microplastics, and they go down to about 10 microns, so 1/100th of a millimeter, that sort of size. So I go to, I can't change it anymore. Yes. Oh, have another technical. Good idea. Okay. Right, let's at least move this bit of it off. No, I can't move that either now. There we go. One feels one should be able to move all this whole thing off, but never mind. Okay. Right, so that's the sort of size of the material we're talking about. And my view is that these are actually much more important than the macroplastics that one can see. So this title says, I can't remember what it says now, but these are basically, these are the primary these are the secondary microplastics. So these are produced, this is one way they're produced by all these other materials that we have, clothing and bottles and road markings and such like, and then they break down and form these microplastics. And they break down as a result of sunlight, wave action, wind, temperature, abrasion and washing. There are also what we call primary microplastics. These are things in our society which already start off as microplastics. These are actually nurdles. That's the sort of feedstock which manufacturers produce in order to send out to plastic manufacturers. Micro beads, most of which are now become illegal, which is good. Pharmaceuticals and toothpaste, all sorts of things which actually start off as very small particles and then flow down into the rivers and into the sea. So the question is, do microplastics pose a great risk? So, is this really a time bomb here, or is it just something which we just have to live with? And so if we are going to understand this risk, we need to think about two things. We need to think about the harm that they might do. And secondly, the exposure. How much are they exposed to in the environment? So thinking first of all about harm, there are two potential areas of harm I like to think of. The first is the ecotoxicology. So that's just how poisonous they are to the ecosystem as they are. And the second bit is what do they do to what we call biogeochemical processes? And I'll say a little bit about that in a minute. So thinking about ecotoxicology. Now, they do contain some quite nasty materials. They got plasticizers, coloring, all sorts of other things in them, which are really quite nasty sorts of materials on their own. They also, some materials stick onto the surface. We call this adsorption. So these are the persistent organic pollutants, endocrine disruptors, and heavy metals. They get stuck onto the surface of these materials. So, we need to be mindful that it's not just the plastics, but it's also, they have some fairly nasty things with them, excuse me, in them or that stick onto them. And some of these certainly, some of them, they do seem to be causing some fairly nasty effects, even in human beings now. So there's one particular one called bisphenol A, which is associated with many types of plastics. And this is a paper I was only reading just a couple of months ago. This has been found in the placenta of women giving birth. And if there are male offspring, the male offspring are lighter than normal. And that's directly related to the concentration of bisphenol A. So here we have, wow, here is a nasty material, which is now in normal society. This is getting into the bodies of women and it is having an effect. So we need to be mindful about this. We need to be careful about it. So there are some possibilities, but we need to be careful about this. So the published studies so far, first of all, they don't use environmentally relevant concentrations. Much of the data that's been published to date, it's completely appalling because they said, well, if we want to see an effect, let's put 10 million times the concentration we've ever found and see what happens. Not sensible, not good. The harm on an ecosystem level has also not yet been shown. The effects of long-term exposure are really unknown. So we are not in a situation where we can say that these do significant harm at the concentrations we find it. And I mean, everything is harmful if we have it at high enough concentrations. Even carrots are. If we eat too much carrot juice, we can kill ourselves. And there are some examples of that. People who've actually become seriously ill by eating too many carrots. So everything's got got its cost. Now, from my own perspective, this is really, really difficult research to do. And my own feeling is that the real problem is going to be prolonged exposure to at sublethal levels. So we end up with a low concentration, but we expose the environment for multiple generations. And the consequence of that is completely unknown at the moment, but there is the potential that it's going to do quite a lot of harm, and it will damage ecosystems. And until we can find good ways of doing this sort of research, and it is really hard to do, then we're not going to be in a good position to make informed judgments. So the potential harms, ecotoxicology and biogeochemical processes, and the most important of the biogeochemical processes is what's called the biological carbon pump. And that is sort of, as written on the tin, that's basically taking carbon dioxide from the atmosphere, taken up at the surface of the ocean, forms particles which settle down under gravitational settling, and that's called the biological carbon pump. It takes material from the atmosphere, it takes carbon from the atmosphere, greenhouse gases, and puts it down into the deep ocean. And this is the most important of the biogeochemical processes that we know of. And there is the possibility, that's exactly what I want. Thank you, John. I was hoping it was concentrated actually, but never mind. It does taste a bit dilute. So there is the possibility that this will be affected. So here are some of these particles. This is fecal material, which I refer to as the fabulous fecal photo, taken by a friend of mine in the States. And this is the material, these are the vehicles by which material settles down through the ocean. And it's possible these will be affected by plastic adhering to it. So I'd only put it in that as firmly as that. There's a possibility that the biological carbon pump will be affected by microplastic contamination. Evidence not strong. So if we're to understand these risks, second thing is we need to know about exposure. How much of this stuff is actually there? So the way people have been studying this, many people have been towing a net on the surface. It's called a Newston net, and they've got some floats here and they drag it along the surface and they measure how much plastic's in it. And you can develop from that a number of maps. And so this is a map here produced by a chap called Van Sabili and showing these large concentrations here. And the total found in the surface layer of the oceans is about 0.2 of a million tons. So that's not actually very much, whoops. And the supply since 1940 is 200 million tons. So it's a very, very small amount which is found at the surface of the ocean using these sorts of techniques. So you ask the question, okay, why is this? And one of the reasons for this is that it's just at the surface of the ocean, and that's not where most of the material is, although we like to think of plastics floating. The other is the size of these particles. So if you remember, I was talking about 300 microns, well, 300 microns for that net. And this is the size distribution. So I don't want you to look at these units here, just the diameter of the particles here going from 1 micron, so that's 1,000th of a millimeter, 100th of a millimeter, 10th of a millimeter. And what you see is this is the number of particles. And as you get smaller, the number of particles goes up and up and up. That's the way marine systems, aquatic systems, if you look at particles in any of these environments, that's what the distribution looks like. Smaller size categories are much more abundant. So one of the reasons why we might not be seeing so much stuff is in the surface of the ocean is because it's all small and we're not collecting it. And the other is that it sinks. So this goes on to the research that my group's been doing. And one of the things we've been doing is to look at various locations in the Atlantic. Here we are in little old England, and here's the trajectory here where we've been taking samples down here and across here using a variety of different ways, from the circles here being taking filters of the water at different depths. The squares are where we've been taking sediment samples, and here these triangles here are where we've been collecting material which is settling down through the water. I'll come on to that in a minute. So we've been doing various things. Now, this is the in situ filtration system that we've been using. So this is a pump here, pumps through a filter up here. We send it down to a depth and it pumps for a while, half an hour or so. And then we bring it up again. And the filter at the top here has then got all the material on it. So we then take that material and we analyze it through this, how did that happen? Through this very sophisticated instrument here, which comes by the very snappy title of a Fourier transform infrared imaging system. I'll be testing on this afterwards, or the FTIR. And we get this lots of data. This is a spectrum here of the material. And from that, we then consult this database that we've got, which, as I mentioned before, is 14,000 different types of plastic. We can then say one particular target, one particular spot has got this type of plastic on it, on the filter. And that's really, really valuable. And the filter moves across and it scans across it to measure all the targets, all the little particles that we've got on it. So that's great. And these are the sorts of things that we find. This is actually at this particular location here, the Porcupine Abyssal Plain Observatory. We've got all sorts of different types: polyethylene, rubber, neoprene, polypropylene, polyethylene acetate, polyester, all sorts of different types we find at this location, so which is quite a long way from land. Most of the water is coming up here. So going back to this lot here, if we look at just a few of these locations here, what we find is that we've got lots of different types of plastic, but in fact, most of it is polyethylene and polypropylene, and all these different other types here are in smaller quantities. And that's not unusual. That's what we sort of expect. The important and the very unusual and surprising thing from this observation is that, so this is water depth here, and this is latitude. So this is down by the Falkland Islands, and this is up by Southampton up here. The very surprising thing is that going down to several hundred meters depth, that's 300 meters there, we're finding significant quantities. So if you remember that map that I showed you, showing that there was all this stuff on the surface of the ocean, this is showing that actually there's a load of stuff below that. And in fact, when you go, this is actually only for polyethylene, but the same sort of story for lots of the other types of plastics. They are found throughout this top 300 meters. Unfortunately, we didn't have enough ship time to go deeper than 300 meters on that particular exercise, but it's showing there's a lot deep down. And in fact, if we look at the number, this is 3 different types: polyethylene, polypropylene, and polystyrene. And going at these different depth bands, you find at the surface there's quite a lot, and then there's a bit less down at that side, that depth there. So this is the depth range is 10 meters, 50 to 170, 150 to 270. But some of them, there's still a lot of material at this deeper part of the water column. So if we look at the polymer groups here, we've got the input of the Atlantic to the Atlantic since 1950 of these different types. And you can, it's pretty difficult to say how much has actually gone into the Atlantic over this time period. You have to make all sorts of assumptions, but we can do some sums. And here we find this is how much we put in to the Atlantic, and this is how much we find there. What's going on here? It looks as though we've got more there than we ever put in. So we have a big problem. What on earth is going on? Why have we got more there now than we think we've ever put in? So some of these, either that's wrong, or we've made a mess of our analysis. I don't think so. I mean, we had this published in Nature, so I think it's pretty robust. So we asked the question, what is going on here? And in fact, the reason I started doing this was because this analysis was very simple. Because I said, okay, we know how much stuff is going into the ocean. If we can find out how much is there now, we know how much is being lost. Simple, nice bit. I mean, I'm not a great mathematician, but it just seemed a pretty sort of no-brainer. How much has gone in? How much have we got? And then we know how long it lasts. And then we find how much has gone in, and we find that we've got more there now than we ever put in. So can't do the sum. So that's the bit that's wrong. And that's why I say we're putting in 10 million tons every year into the ocean. it could well be 5 times that amount, and we're just not doing the accounting properly. So cones, they're a bit like rain gauges. They just collect a load of material, which comes down, and it gets, internet connection is unstable. So sorry. And the material gets collected in these little cups here, which move on every 2 weeks. So I've been doing this for the last few decades, and at 3,000 meters depth. And as a result of that, we're just in the process now of doing the analysis to find out what is in that material we've been collecting. And that means we're going to have a time series going back to 1989 of how this has changed over time. So it's really, really important to do that, looking at these historical data. Similarly, we've been looking at the sediment. So this is what's called a multi-corer, goes down onto the sediment floor. Then this whole set of cores here sinks nice and slowly into the sediment, and you get these cores, these sediment samples, and you do that down to 5,000 meters depth, whatever. It's not difficult, it's agricultural. And as a result of that, you find, even in the sediments, you've got all sorts of bits of water. This is actually from the Tyrrhenian Sea, which is the sea just to the west coast of Italy. So we've not got very much data from the sediments. This is the locations where we've got sediment samples. Just have a look at the Pacific here, middle of the Atlantic. Oh, dear me, really, really small amounts of data. So we've got a real poverty of data. So, but once again, this is going back to this basic question, which I say that I tried to ask. Well, I did ask the question, didn't get the answer, which is how long does this stuff last? And everybody says, yes, it lasts 1,000 years. I don't believe it does, but at the moment, not in a very good position to say, I think this is the number. And by the environmental half-life, what I mean is, if we had, let's say, 100 tons in a volume of seawater, how long would it take before there's only 50 tons left? It's the half-life of that material. So that's what, for those of you who know about radiochemistry, that's the sort of where that term comes from. But it's basically how persistent is it? And before it either goes into the geological sediment, so it won't be, the next time it comes out will be in a volcano in 20 million years time, or till it breaks down into carbon dioxide and water. So I think we'll skip on these. Well, I would if I could, because this has gone on too long. So this material, it also moves about under the influence of water movements. And this is a rather nice, rather nice little modeling output that my friend Andrew Yule did. So these are particles. They happen to be in the range in our, according to the logo of my organization, but which he's put at 1 meter depth. So there's, I don't know, 10,000 particles there, something like that. And what this model shows is what happens to that material over a 10-year period. And there we go. So, and right, we'll just try that once more, shall we? See if it works. If it doesn't, too bad. So, and the color of this indicates its depth. So what you can see is that quite a lot of the material stays at 1 meter depth, and quite a lot of it goes down, down, down into these deeper depths. So these colors, the greens and the reds, but also that this stuff goes all over the place. So over a 10-year period, it's getting right up here, up into the Arctic, into the Labrador Sea. It gets all over the place. So the currents of the ocean, and John, of course, knows a thing or two about currents, this takes this material all over the show. So some crucial questions. And this is my semi-final or third from the end slide. How much microplastic is in the water column and the sediments? Such basic, simple questions that we don't know the answer to. How much is there, for heaven's sake? What are the characteristics of this material in terms of the type of material, the size distribution, shape, etc.? How do these microplastic characteristics change over space and time? Also, very, very poor data on such simple questions. You don't need to be a scientist or, to understand this is just basic stuff. How much is there? What are the processes that determine their distribution in space and time? Water currents, as I mentioned just now and showed, Yeah, they move it around. What happens at the estuary of rivers? And one of the programs I'm involved with, an EU program just now, I'm actually working in the Thames and going into the Thames, Southern North Sea, and then into the Atlantic. So what processes determine this distribution, and what are the principal source regions and human activities? So really, really simple, straightforward question. And then the other side of that coin is, what harm do they do at the concentrations they're found? As I've said earlier, a lot of rubbish science being done by people saying they want to see an effect, and therefore they're going to whop up the concentration in their experimental chamber to 10 million times, 50 million times what you'd ever find. And then sure enough, it has an effect. So those are really simple questions. So on the positive side, what can we do now? So for starters, we can use less. And if we use less, and that means when we go into the supermarkets or whatever, we don't buy the ones which have got too much plastic wrapping. Simple, use less. And markets, of course, respond to that. If we vote with our feet and we don't buy this stuff, then the people who are selling it will say, oh, why is nobody buying this? But use less. Reuse. The plastic bag tax was supposed to have had a very positive effect on that. We're reusing our bags and the bags for life. Actually, that hasn't worked. I mean, everybody thinks it's worked because we had an 80% reduction within 2 years, 80% reduction in the number of plastic bags, but everybody was buying bags for life. So just last year, believe it or not, the amount of bags for life which were bought is equivalent to 57 bags per household. What? These are bags for life. These are supposed to last you the rest of your life. So remember to take your bags for life, to take them, to use them. Don't just go in and then buy another one. That's not a sensible use of this resource. So the plastic bags tax, which I was really enthusiastic about, really hasn't worked. It might have changed some people's mindset, certainly has. We need to recycle properly. Recycling is not always easy, particularly when manufacturers produce plastics which are difficult to recycle, or they have mixtures of plastics. You know, your typical single-use plastic bottle, it's got at least 2 different types of plastic on it. That makes it difficult, the cap and the bit underneath the cap. So, and then you can use it for energy generation. Not very smart, but okay, that might have a role. And then dumping it, but very, very carefully. Dumping it in landfill, that's a very, very bad idea. This is a resource we should be careful of. So reasons to be positive. I said I'd end on a positive note. The first is that there is pressure to change personal behavior. The plastic bags tax hasn't worked properly, but people's personal behavior has changed. Secondly, enthusiasm to clean up the environment. Great. I mean, I'm not actually of the view that cleaning up the environment is possible for these microplastics, which are the ones which are likely to do the most harm, just because they're too small. Some of you might have heard about the Pacific garbage patch and attempts to clean that up. Nah, not a good idea. Enormous amounts of carbon dioxide released if you're going to send all these ships out to go and collect this stuff. Bad idea. So cleaning up the environment in general, a good idea, but let's be very smart about the way we do it. Reaction of manufacturers and suppliers, yes, they realize because of public pressure, they realize that they need to get their act together, they need to be smarter, they need to produce better materials, and they need to be legislated, probably. Combination of public pressure and legislation is what I feel is the most likely to be the best way forward. There are examples of manufacturers being really duplicitous in the language they use, referring to bioplastics or biodegradable plastics. Some of these so-called biodegradable plastics, the only way they are biodegradable is if you put them into an industrial biodegrader, 70 degrees centigrade. That's the only way they break down. So this is duplicitous on the part of the manufacturers, and we need to be very mindful of that. So we need to have legislation, and there are developments in material sciences, which is great, producing new novel materials, which are going to be much better for the environment. So, And then the development in environmental science, such as I and my group are doing. This is a good way. We're getting some funding to do that. So, and my last slide is the extremely positive one. And the reason this is positive, have you had your dinner? The reason this is positive is this is horse manure. And this is New York in 1887. And in 1887, there were 100,000 horses in New York, producing 1,000 tons of horse manure every day and 97 dead horses. This was an absolute catastrophe for New York and all the major cities as well. So there was a conference set up in 1889, international conference, 3-day conference. How are we going to deal with this colossal amount of manure, which is clogging up our cities and the enormous problems of health problems, rats, etc. How are we going to deal with this? 1889, they had this international conference, 3-day conference. They gave up after halfway through the second day. We can't do this. It's impossible. It's an impossible situation we're in. And then we have the internal combustion engine coming along, and which produced its own little problems, which we all know about. However, mankind can think laterally. We can think imaginatively. We can find solutions to problems. And the solution to this problem was the car, but it did get solved by our ingenuity. So I'm very much of the glass half full type of person, and I think we will find solutions to this as long as we as individuals modify our own personal behavior and also pressurize either by our purchasing options or by directly influencing the policymakers and the legislators so that they do the right thing. And that is not easy, but I would encourage you all to do exactly that, modify your own personal behavior and lobby, pressurize both legislators, policymakers, and industry to change their behavior. So thank you very much. I'm very happy to answer questions.